On paper, this rescue shouldn't work. It's 40 degrees Celsius in the Persian Gulf. Air density has dropped almost 15% compared to standard conditions. To generate the same lift, the rotor must accelerate more air downward, which, according to actuator disk theory, demands dramatically more power. The induced power required scales with the 3/2 power thrust divided by the square root of density. In hot, thin air, the engines give you less power while the rotor demands more. This is a physics wall that has doomed helicopter rescues for decades. Yet in the Hormuz Ultimatum scenario, U.S. Marines fast-roped or were hoisted out of harm's way from a UH-60 Black Hawk. How? That's the engineering story we're about to unpack. First principles only. Map of Strait of Hormuz with oil tanker routes highlighted. Archival clips of UH-60s in desert ops. Split screen. Fixed-wing jet versus hovering helicopter. The Strait of Hormuz is the world's most critical maritime choke point. 20% of global oil passes through it. In a crisis, you cannot wait for a runway or a ship to come alongside. You need vertical takeoff and landing, precise hover, and the ability to insert or extract personnel in seconds. Fixed-wing aircraft cannot loiter at zero forward speed. Ships cannot reach shallow or hostile shorelines fast enough. Only a helicopter gives commanders that instantaneous, anywhere, now capability. The Black Hawk was designed from the ground up in the 1970s as the Army's replacement for the Vietnam-era Huey. More power, more lift, better survivability, precisely to meet these kinds of high-threat, high-temperature extractions. Side-by-side comparison, UH-1 Huey versus UH-60 rotor disc. Animated momentum theory. Induced velocity V equals square root T/2 rho A. Graph of power required versus available at sea level 15 degrees Celsius versus 40 degrees Celsius at 0-foot altitude. Real Black Hawk hover performance charts from flight manuals. Let's go to first principles. A rotor in hover acts like a giant fan. Momentum theory tells us the induced velocity to the disk is V equals square root T/2 rho A, where T is thrust equal to weight. Rho is air density and A is the rotor disk area. Induced power is then roughly T times V, so it scales as T caret 3/2 / square root rho. In Hormuz summer conditions, rho drops sharply. To hover at the same gross weight, the pilot needs roughly 20 to 25% more power just to stay airborne. Add external stores, Marines in full kit, and the fact that you're often operating out of ground effect, OGE, over water or uneven terrain, and the margin vanishes. Worse, forward flight brings dissymmetry of lift. Advancing blade sees higher relative airspeed. Retreating blade sees less. Without careful blade design, the helicopter would roll uncontrollably. Early helicopters hit retreating blade stall limits, fast in hot/high conditions. The Black Hawk had to solve both hover power hunger and forward flight asymmetry at the same time. Exploded 3D model of UH-60 main rotor head, elastomeric bearings, fully articulated. Slow motion of wide-chord composite blades in flight. Cut to canted tail rotor animation, showing vertical lift component. CFD of blade tip vortices with swept tips. Sikorsky's answer was ruthless optimization of the rotor system. Disc loading. 53 feet 8 inches, 16.36 meters. Diameter 4-bladed main rotor gives a large A, lowering the power penalty in the momentum equation. Blade design. The UH-60 MS wide-chord composite blades, SC-1095/SC-1094, are 8 airfoils, 20 degrees swept tips high twist, increase solidity and delay stall on the retreating side while reducing tip losses. Each extra 4 to 5 inches of cord added hundreds of pounds of lift at the same power. Fully articulated head with elastomeric bearings allows each blade to flap, lead lag, and feather independently without metal hinges that wear out. Smoother control, less vibration, higher maneuverability in tight rescue hover. Canted tail rotor, not just anti-torque. The 4-bladed canted unit produces 400 to 500 pounds of extra vertical lift, effectively giving the aircraft a bigger rotor disc without adding main rotor complexity. It also improves center of gravity flexibility for fast rope or hoist ops. Twin T700G 701D turbo shafts. Each delivers up to 2,000 shaft horsepower. In the M model, Combined with improved gearboxes and active vibration control, the aircraft can sustain OG hover at higher gross weights and hotter conditions than its predecessors. Result? The Black Hawk can hover at 18,000 to 19,000 pounds gross weight in conditions where older helicopters will be power limited to 12,000 pounds. Fast rope insertion or rescue hoist extraction becomes possible even when the air itself is fighting you. Graph: power required / available curves at different temperatures. Fuel burn rate animation, hover versus cruise. Infrared signature comparison before / after upturned exhaust. Cost per flight hour overlay. No engineering solution is free. First, power hunger. In a prolonged hover for hoist rescue, you can burn 800 to 1,000 pounds of fuel per hour, far higher than cruise. Mission planners must leave enough margin for the return leg or risk becoming a stranded asset themselves. Second, noise and infrared signature. That big rotor and powerful engines make the aircraft loud and hot. The upturned exhaust and composite blades help. But the Black Hawk was never designed for stealth. It trades low observability for raw lift and ruggedness. In a contested Hormuz environment, that means relying on escort speed and surprise rather than invisibility. Third, maintenance. The advanced rotor head and digital flight controls are reliable, but when something does break in the field, the parts count and tolerances are higher than a simple piston helicopter. Operating cost hovers around $3,000 to $6,000 per flight hour, depending on variant and mission profile. Real engineering is compromise. The Black Hawk is faster, stronger, and more capable than the Hewitt replaced, but it is also heavier, thirstier, and more expensive. Reconstructed sequence. Black Hawk approaches hover. Fast rope deployment. Marine sliding down. Hoist recovery. Slow motion blade flex under load. Pilot view with glass cockpit overlays. In the Hormuz scenario, the aircraft approaches low and fast, then transitions to a stable OG hover, using the digital flight control system to hold position within feet despite gusts off the water. Marines fast rope in seconds, or the hoist operator lowers the rescue basket. The canted tail rotor and articulated main rotor give the pilot precise yaw and roll authority, even when one side is loaded asymmetrically. Once the team is aboard, the pilot pulls power, translates forward, and the aircraft accelerates away, using translational lift extra efficiency once moving, to climb out of the danger zone. Side-by-side performance tables, UH-60A versus UH-60M versus future concepts. Cost-benefit graphic. Closing shot of Black Hawk formation over open ocean at sunset. Is the UH-60 viable for future? Absolutely, but only because continuous upgrades keep pushing the physics envelope. The M model's wide-chord blades and 701D engines brought back the performance lost to modern armor and electronics. Next steps, T901 engines, even smarter rotor controls, will squeeze a few more % out of the same laws of nature. Economically, each aircraft costs tens of millions to acquire and thousands per hour to fly. But when the alternative is losing strategic assets or personnel in the world's most vital energy artery, the cost is acceptable. The Black Hawk isn't cheap. It is the minimum price physics and geopolitics will allow for reliable vertical rescue in the harshest conditions on Earth. Montage, historical Huey in Vietnam, modern Black Hawk in desert, CFD animations fading into real flight footage. Text: engineering doesn't defeat physics. It negotiates with it. Nature sets the rules, density, momentum, stall angles. Engineers don't break them. They design around them with ruthless precision. The UH-60 Black Hawk doesn't hover in the Hormuz heat because the laws of physics changed. It hovers because every blade angle, every ounce of engine power, and every gram of composite material was chosen to make the impossible merely difficult. And that is why, when the next ultimatum comes, the Marines will still ride the Black Hawk in and out again. Subscribe. Sources. Next episode: the physics of hypersonic interceptors.